unit today, and it is patterns and inductive reasoning. So this is lesson 2.1. So for part A, I want you guys to just look for a pattern. There's clearly a pattern here. What are the next two terms in the sequence? Anytime you want to, pause this video and check, then fast forward and see if you did it right. But it's a good idea to think through these by yourself. So push pause and see if you can figure them out. Maybe go ahead and look at A and B. Oh, A, B, and the next one down here. All right. These to me look like they are multiplying by 3. So each one of these did times 3, times 3, times 3. So the next three numbers, if you multiply by 3, would be 243, then 729. Oh, it only wanted the next two. All right. On part B, we're looking for a pattern. I see a triangle in a circle, which has 3 sides. Then I see a 4-sided shape in a circle. Then I see a 5-sided shape in a circle. So the next one would be a 6-sided shape, which is not going to be very good, but that's okay. You get the point. And then a 7, oh my, that's even worse. 7-sided shape in a circle. All right, the next two terms in the sequence down here, 45, 40, 35, 30, it looks like they're subtracting 5 each time. So the next two terms would obviously be 25 and then 20. All right, what you guys have been doing is just patterns. Now we're going to talk about inductive reasoning. So I want you to know what the word inductive means. To use inductive reasoning, it basically means creating your own hypothesis. So this is just basically what you think. It's a good guess, but it's not necessarily proven using definitions or facts or equations or anything like that. Basically, inductive is you're looking at something and you're creating your own hypothesis. That's basically, inductive is basically a really good guess. So it's basically not proven, but it's something that's probably correct just based on a good guess. Okay, so let's look at the circles. What conjecture? Conjecture's new. A conjecture is basically a rule. So what rule can you make about the number of regions 20 diameters form? So they're jumping all the way up to 20. So a diameter, obviously, again, is the distance across a circle. This one only has 1 diameter. This one has 2 diameters drawn in. This one has 3 diameters drawn in, and they want us to jump all the way up to 20. So what rule can you make? Pause the video and kind of think through this. If you're ready to move on, here's what I think. For a 1 diameter, it separated this into 2 parts. For a 2 diameter, it separated this into 4 parts. For a 3 diameter circle, it separated this into 6 parts. So regions is what they're talking about. Regions is parts. So here's what I think. I think that all we're doing is multiplying the number of diameters by 2 to get the number of parts or regions. So if we had a circle that had 20, whatever. I'm not even going to count these, so don't go through and count them. Let's say it was definitely 20 diameters. I could multiply it by 2, and it would be 40 parts, or 40, regions. So my conjecture is that it would be 40, because it's 20 diameters times 2. All right, let's look at the back. So on the back, what conjectures can you make about the sum of the first 30 even numbers? Oh my goodness. Okay. So I need to make some type of a table here. So in my table, I want the sum of the first 30 even numbers. So let's see. How would I even set this up? Let's do 1, I'm going to need a little bit more space for 2, a little bit more space for 3. I'm only going to do a few, and then we'll see if you guys can figure this out. So the first 30, even numbers. Okay, so the first 30 even numbers. So the first even number is 2. And the sum of that is just 2. In my next table, in my next section, I want the 2 even numbers. So those would both be 2, and the next even number would be 4, which is going to be 6. All right, the next term would be 3 even numbers, so 2 plus 4 plus 6, and 2 plus 4 plus 6 is 12. Okay, in our fourth section of the table, I would do 2 plus 4 plus 6 plus 8, which that is 20. In the fifth one, I would have 5 terms, 2, 4, 6, 8, and 10. And that would equal 30, I believe. Okay, and we could keep going, but we want to know 30. And so I really just want to come up with some type of a rule so I can just skip to 30 without having to do 2, 4, 6, 8, 10, 12, 14, 16, all the way to 30 of them. So let's look. Each one of these, let's see. I'm actually thinking, actually stop the video and think if you have an idea to figure out what's happening here so that we could jump to 30. If you're not pausing the video, I want us to try to see what we can figure out from here, the first number in our table to get to 2. The second term to get to 6. The third term to get to 12. The fourth term to get to 20. It looks to me like I, from here to here, did 1 times 2 to get this answer. 2 times 3 to get this answer. 3 times 4 gets me this answer. 4 times 5 gets me this answer. So we're adding 1 to each previously multiplied answer. If you're setting that up in an equation, it would look like y equals, this is our y, whatever we're getting, it equals a number times a number added to 1 from the previous term. Okay, just think that through for a minute. If you need to go back and plug these in to try this out. But this is a fancy equation which works. So if we need to solve it for 30, let's, I'm going to go ahead and plug in 30 for both of these because we want to know 30. So 30 times 30 plus 1. So 30 plus 1 is 31. So I would like to know what 30 times 31 is. I don't know. 30 times 31 is 930. I am so glad I didn't have to count that far. So coming up with a rule or a conjecture is very helpful when you're talking about really large sums. So 30 would be 930. All right, the backpack sold one we are actually going to skip because this one is very similar to one that we're going to do later, and we'll work that one out later together. So skip the sales question. I want to go talk real quick about finding a counterexample. So a counterexample is something that proves a conjecture false. So for example, there we go, proves it false. So a counterexample would be like if I said it's not going to rain today, and you went outside and showed me a picture of the outside and it was raining, that would be a counterexample to be able to prove me false. So let's talk about what a counterexample would be for each conjecture. So A, if the name of a month starts with the letter J, such as June or July, it is a summer month. Is that true? If it is, then we can't come up with a counterexample. But if it is false, we can come up with a counterexample to prove this conjecture is false. So think about it for a minute. There is also another month that starts with a J, and it is January. January is most definitely not a summer month, so we have just proven this conjecture false by giving a counterexample. So don't just say it's false. Give a counterexample that proves it's false, like January. All right, let's look at B. You can connect any 3 points to form a triangle. Any 3 points to form a triangle. Okay, yeah, normally yes. 3 points, boom, there's a triangle. But we're trying to provide a counterexample. Is there another example that has 3 points connected that does not make a triangle? Right away, I think of 3 points on a line. Okay, there's 3 points connected, and it is not on a triangle. So here is my counterexample. All right, and then the last one, a counterexample of when you multiply a number by 2, the product is greater than the original number. So basically they're saying take any number, let's say 5, times 2, and the product of that is greater than the original number. So yeah, most of the time that is very true. So what is a counterexample that would prove that this is not always true? I think right off the bat of a negative number. So -3, for example. When you multiply that by 2, it does not get greater. It most definitely becomes smaller. -6 is much smaller. So this is my counterexample.